Okay.
So, okay,
Yeah,
so
this, by the way, Daniel, Discord might make the audio more because there's a big lag, I think.
yeah, there's a big lag, but I think it's gonna be fine.
You
Let's
think
see.
it might be? Yeah. It should be fine. Okay.
Okay, so because
We're gonna have to instruct. Yeah, go
before
ahead.
the voice was coming through clean, but now it's not. But let me see if I can quickly just close Chrome because that should make things easier. And there's a delay anyway in the stream, so let's see if because I got it open just on my phone to check
Mm.
whether this is really working. So it seems to be loading now. Oh, 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 oh. Okay, so it seems we're live. And I have it open here in case someone's using the chat, because if I have Chrome, it just doesn't work. Maybe just say hi or something so I can see, I can hear whether the voice is coming through well.
Hey. Heyo.
Okay, cool.
We're
Let me
live.
just.
Test, test.
Yeah, nice. Okay, cool. So it's coming with a bit of a delay, but that's good. I set it up on purpose like that, so it's okay. Perfect. Cool. So yeah, pretty much for me, it's like every time I do a live, it's a bit of a new adventure. So I apologize up front to anyone who's watching if the whole thing just breaks and it goes black. That I don't know. We'll figure out. Maybe we can do an offline version of these one day, or I don't know. It's just I'm really happy that you guys made it to to join these because I did some of the puzzle streams before, but they were a bit more like offline, and I want to kind of do something live because of this is also something that I'm doing around trying to help the Quantum Odyssey team to market the game and sell the game, and then people who will just be watching the stream and maybe buy the game will use part of this revenue will actually go to the Unitary Fund, which is a fund that basically invests in small projects related to quantum computing. Projects which would typically, just not get any funding because it's just like a one-man show or like small things like that, quantum education, stuff like that. So, yeah,
Yeah.
basically,
Unity.
if anyone's watching wants to buy the game, you can do this also after the stream, and you just need to go to the web page that's like in the description of the video. The game is free to download, and it's also free to play. The introduction of the game is free to play, and only when you go past the introduction you have to pay for sort of the actual different levels and puzzles. And with a code, I think it's ANSYS50, you get 50% off the price, which is a good deal. And yeah, and with the revenue that we make, we're going to make the donation. So, and we're doing this sort of December, January, and maybe a little bit of February. We'll see with different people. Yeah, so I hope you guys can see the game, right? So at least big enough in the screen. I don't know if the sound is. Do you hear the sound of the game? Because last time I did that, the person I was doing this with didn't. Okay, cool, perfect. So because of the whole setup, it might be that while we load the puzzles, the game takes like 30 seconds or a minute to load. But that's not a problem because I am really curious to know about a little bit more about you guys and actually have a couple of questions that if you are not ashamed to answer, then that'll be cool. So,
Bucks.
I mean, first,
Absolutely.
awesome. First of all, the game. If you hit play, you just go to the normal main levels. But we'll just go to the solve part where you can actually see the different puzzles that I've been preparing. So EBs for Eigenbros, by the way, for I mean, I don't know. I think we've got similar size audiences, but I don't know if there's an overlap or not. So if you guys don't know Eigenbros, just definitely go and check them out. Subscribe. I think you're all over the place. Twitter as well. I don't know. You guys, you probably know better, so you can share that as well if you want.
Yeah, so just check out eigenbros.com, Eigenbros Twitter, Eigenbros Instagram, Eigenbros TikTok. What else? Did I miss anything, Juan?
I think Eigenbros pretty much on every social media
Yeah.
platform besides TikTok.
And
TikTok
we're basically
Eigenbros
just a
too.
physics podcast. Sometimes we just BS around. So,
Yeah.
But you
we
guys
like science.
you guys were on TikTok, weren't you?
Yeah, we're on Eigenbros 2 on TikTok.
Ah, okay, cool. Is it
Yeah, I
difficult to
messed up.
manage all that?
I'm sorry?
Is it difficult to manage all that social stuff? Because that's something that I'm considering as well. I'm just basically just a Twitter solo kind of.
It is if you have a job.
Okay.
So I am currently unemployed, so I can do all that.
He's fun employed.
Unemployed, baby.
Okay. Okay. That's good.
He gets to manage, so
Sorry, say that again.
no, he gets to manage the brand. It's a
Mhm.
full-time job managing the Eigenbros brand, and he has to cradle it and hold it like a baby.
Yes.
Sometimes
that-
he drops the.
Yeah, that's why you have to do the apology or the sort of the video that you do with the Twitter thing, right?
We're learning. We're
Yeah.
learning as
happens to the best. I mean, it just I'm listening to your podcast a lot while I do the dishes in the evening or stuff like that. I just put the headphones on and I just find
great.
I just some of those episodes is just like really great to listen to. So I definitely recommend that. I'll just start loading the first puzzle because it's going to be while we wait just to give a bit of context. So I mean, you guys are physics. I don't know what students, PhD students. I have absolutely no idea how the system works because I haven't like the last time I stepped into university was like 2012 or something.
So of course we're in the United States. I was a physics graduate student, so I no longer. That's how I'm doing all the social media and all that stuff. But I was a condensed matter physicist, just like Juan. In a PhD program. We come from the same program. But yeah, and then Juan is actually still actively doing his PhD.
Okay, cool.
trying.
Try. And you decided to start the podcast just because you're bored or you just like.
Yeah, pretty much. One of the reasons we really wanted to start it was because during the time, me and Juan were really just kind of depressed about like how much we were studying and learning stuff, but we weren't actually giving anything back.
Yeah.
So the podcast was a way for us to kind of, at the time, it was to talk about stuff actually not as much physics and just to kind of just have fun with it and put something out in the world and maybe give advice to undergrads and people who are just starting off in physics.
Yeah.
And yeah, it was mostly fun in the beginning.
That's, I mean, it's something that it's something that I ask always when I meet people that are like running YouTube channels or stuff like that, because for me it was a bit of I mean, actually I kind of think a bit of similar in the sense that I really felt like I wanted to do something a bit different, kind of like I was a bit bored with what I was doing just as part of the regular job, and also share stuff at the same time, right? So kind of trying to be useful. And so I said, why not learn something new and then try to share that with the world? So I think that's it's pretty nice. Let me just explain you real quick what is this about, right? So we'll do a couple of puzzles first, which are really introduction. I hope the background sound is not bothering you too much.
No, it's
Okay, cool. So the idea is, and you know more physics than I do because I have not, like I have a master's in computer science, and I'm in quantum computing since like May 2019 or something like that. So not really, and I haven't done any of the physics behind this, just the pure computing part of. So, but basically, you've got this funky machine here, which is supposed to be a sort of a quantum system, right? Like the top part is like your initial state of the system, and the bottom part is the goal or the end state of the system. So what you see here with these bowls is where I want you as a creator of the puzzle to take the state to, right? So your initial state is this is a 2-qubit system, so it's got like it starts in the 0, 0 state, right? It's got 2 qubits, and so you have to take it to the 1, 0 state. Does that make sense?
Yes.
okay. Yeah.
So the
So
way
how do we take?
Yeah, so the way this works is like you have basically your standard quantum computing gates that you can use, right? So the Hadamard gate, the Z gate, the Y gate, those are gates that you can apply to each of the qubits and transform their state, right?
Okay.
Now, the beauty of this game is that, usually the hardmark gate is represented with a matrix, right? And so the beauty of this game is that they have a nice visualization of what each gate does. So it kind of helps you as well intuitively to see what the effect is gonna have that gate without really taking a look at the math underneath, right? So that's the idea. So this is the first puzzle, and maybe the idea of the whole show is you tell me what pieces you want to put where, and then we try to get the puzzle solved. The first 2 or 3 puzzles will be really just to warm up, and then I prepared the more complicated one for you to suffer a bit more.
Oh no, Daniel! Are you gonna make us think?
Exactly.
Relaxing.
It's relaxing. Yeah. So feel free to let me know what would you like. What's your first move for this puzzle? I can help you in the warm up. I can help you out if you're not really feeling like warmed up enough. But it's yeah.
I'm just not sure I presume these drag and drop gates are supposed to be like operators that put you in different states.
Yeah, so if I recall, the Hadamard gate is the one that puts things in superposition.
Exactly.
The Z, the Y, and the Z. X just will flip the state on an axis, I guess. And then the S is, what is the S? I don't know.
Spin state or something?
So the S is a sort of a half of the Z gate, so to say. It's a square. Is it like the square root of the Z gate? Kind of. So it's like you do half the effect of the Z gate. So you got it right. So basically, we see here zeros and ones, right? So we have to remember that in sort of the default way of measuring a quantum system is using Z measurements, which basically it measures, if you imagine the spin of like an electron or a particle or something, it's +1, -1, and then it maps these to 0 or 1. So but at the end of the day you have a 0 or 1. And so, for example, what the X gate will do, if I drag the X gate, that's the Y gate. If I drag the X gate to qubit 1, right? Oh, now I solved the puzzle for you. Sorry. Yeah. So it basically flips the beat, right? So it flips. Let's see if I can. Yeah, we can actually go to the next one, and I can keep explaining that.
I don't understand. So okay, so it flips all of the states. So you have 0, 0, 0, 1, 1, 0, 1, 1, or something. It flips all of them.
Yeah, exactly. So basically, let me open another one, and we can play with the gates a little bit more in detail. So we'll open the second puzzle, which is also a warm-up. So basically the idea is you have 2 qubits, right? But each qubit can be in the 0 state or the 1 state or a linear combination of both. So what this means essentially is that when you measure a system with 2 qubits, you can have 4 possible states that you measure, right? So you can measure either both in the 0 state, or both in the 1 state, or one in the 0 state and the other one in the 1 state. So you have 4 combinations. It's like 2 to the power of the qubits that you have. So if you place an X gate in the first qubit, you'll basically flip the if your qubit is in the 0, 0 state, you will flip that 0 to be a 1, right? So you're flipping the value of that qubit, which means that whenever you are in your states. So here we have, for example, let me just open this. It's a bit of a different goal here, right? So. But we can play with the X gate again, just to make sure that you get the intuition behind this. So if I put it here, this is qubit 1. So what it does is it flips the first qubit to become 1. So it goes from the 0, 0 to the 1, 0 state, right? If I were to
now, why are they all like crossing paths here? I don't understand that.
Because if that's supposed to give you a view on the overall system. So if your initial state would be 1, 0, then the same gate would make it go from here to 0, 0, right?
Mm-hmm.
Does that make sense? So it's the lasers are supposed to show you how would the entire circuit evolve or the system evolve, regardless of where your initial state is, right? The moving ball indicates what your initial actual state is, right? But if you were somewhere else, you would go somewhere else. That's why this is creating this mesh. So if I would now, wait a second.
I was going to say, like, visual representation of like your states transforming, I guess, or something. I don't know.
Exactly.
Okay.
Yeah,
So
I'm
if
just trying to also figure out then how do you know what state you want to get to? So let's say if you start with the 001, how do I know I want to go to the 10 state?
So I mean, the place where you want to go. This is something that I give you as a target of the puzzle, right? So this display at the bottom tells you what is the target state that you need to achieve to win the puzzle. So I want you to take the system from the state 00 to the state 00, but the color is different. These colors represent the relative phase of the state. Right, so I don't know if you remember this or if you know this. So a quantum state that is in superposition, for example, one qubit in superposition is in the 0+1 state, but it can also be in the 0-1 state, right? So that means the one component has a relative phase of like 180 degrees, and in this game, that 180 degrees phase is represented by the color red. So the phases are represented with a color code, right? And that's why you see also that the Z gate here is drawn like two vertical lines. The one on the right is red because it means that it turns the one component red. Yeah. So the S gate turns it green, right? Because it's so it's kind of half red, so to say. If that makes any sense. The idea is if you apply two S gates in a row, you will turn the phase red. That's the sort of the idea, right? So in this case, if I would apply another X gate here, right, that would change the mesh, and actually it will take the state from the 00 to the 11.
Right.
Yeah, it takes a bit to get used to it. Also from this visualization perspective, it's not that straightforward. But once you get it, it's intuitive.
Yeah, I think I'm understanding. I still just don't understand though how I know what my goal is.
So your goal is So your goal is to create a state that follows these. So do you see the red ball here?
Yeah.
That's your goal. So you want to take your blue ball that starts at the 00 state. You want to take it down to the 00 state, but big red. So you wanna put it there, and along the way you have to change the phase so it's red.
So let's see then. What should we do? So let's think about this. So
I'm gonna remove the X gates, right? So now you have to tell me what gate or gates you want me to apply to achieve that goal here.
So I'm thinking, should we just put a Z gate on there?
Z gate.
Let's put a Z on.
And which qubit
on that, baby.
Yeah, which qubit do you want me to put it on? 1 or 2?
On qubit 1.
So.
Oh no!
Remember,
let's see what happened.
Yeah. So remember that this only turns the phase for the part of the qubit that it's 1. So it means that if you put it in qubit 1, it will only affect these two states where you're not in, right? So.
Interesting. Okay, so we want to remove that Z gate then, and we need to take it to where
no, wouldn't you put it on like the 2 qubit? The qubit 2? Or no? Am I understanding that wrong?
Well, I think he said the Z.
So I put it to the
one.
No, 1.
Okay, no, it's not gonna work. No, don't do it. Don't do it.
The delay.
Yeah.
Right. So the Z only affects if it's in the one state. So let's try an S then. Can we try an S on qubit 1?
Yeah. So it basically does the same, but the phase color is different, right?
Ah, okay. So the phase changes for the one
A quantum
state.
system.
Both of these. Flip the phase. Okay. So can we undo S from qubit 1?
Yep.
So sorry, Daniel. We're trying to just figure this out.
It's all, you can also you can also try to think out loud. I can help you out if you need any help, because it's really unintuitive at the beginning. But you have to think about that restriction, right? That the gates that change the phase only affect the states that are 1. But you can always take one qubit sort of aside and then put it back in its place, right? So you can apply a gate as many times as you want. So that's maybe a hint there.
Yeah, so I'm thinking what we're going to do is we're going to need to change both those 0 states to 1s. And then we're going to have to do then we can maybe try a Z flip on both those states. And then
So if I do this and now I apply a Z gate, or where qubit 1 or 2?
On 1.
Yeah. Can we do it? Is that it?
And 2, I think, right? We need 2.
Ah, damn it.
So now it's red. Now it's red.
On 2 as well. Okay, let's take it in.
What do you want to do now?
Can I apply a Z on qubit 2?
No, we're so
Oh,
close.
that's not it.
That's not it. I mean, you had the ball red already, right? So if I undo these, you kind of you got the right phase. Now you just need to put it back into the right place. So you can still apply more operations after that, right? It doesn't have to be another qubit.
Let's do X again.
Yeah. So if you
I
do
feel like
another one, or
oh, what?
Yeah.
Dang it.
Another one on qubit 2.
exactly.
I think you got it.
I think we got it.
You got it. You got it. That's perfect.
Yeah.
Sweet. Still don't quite get what we did. Hell
Okay,
yeah.
let's sit down and digest this. Me and Terrence want
Yeah,
to
we
take
need to
time.
go over
Take the time to think about what happened.
Okay, so we started off with 2 zeros, right?
Yeah.
Then we applied the poly Z gate, or what did we do? We applied the
We flipped the polarity.
X gate. So we applied
sorry,
the X gate. That changed the state to 1 for both qubits. Then we applied the phase change with the Z gate, right?
Flip it, yeah.
But then what did that flip that to? It flipped it to
Red, but it still had the same path.
So what was the qubit number? Was it 1 0 or what?
So the target qubit was 0 0. So you kind of had to go back to your initial setup, but you needed to change the phase in somewhat in between. But there's no gate that changes the phase of the 0 component, the relative phase. It's just by definition. So the way that you do that is you kind of create this pattern, which is like a sandwich of 2 different gates. So you first do an X gate or 2X. You could also have done just 1 X gate, for example, to qubit number 2, then apply the Z gate to that same qubit, and then apply also just 1 X gate to go back to the 0 0 state. So you're kind of undoing the initial step, having changed the phase in between.
Yeah.
So you kind of have you have to think about. Yeah. Say that again.
I said, but we still got rank 5, so now who's laughing?
So
Yeah. The game thinks we're great.
exactly. So let's go to the next puzzle.
Oh yeah, right. Yeah, let's do it.
Let's go to this is the last warm up, and then this is the last warm up, and then comes the real one.
Oh.
All right, so we better get it this time.
Yeah. Let's
Okay.
let's try to minimize our paths, Terrence.
All right, let's do it.
We should be able to do it. We have 2 quantum brain.
2 quantum brain. Actually, I have a question. I have a question for you guys. So I think the first episode that I watched was actually your interview with Grant Sanderson, and I was trying to look at what was your first video, and I realized that there's no episode 1. It doesn't exist. What happened to it?
Right. Oh, the mystery of episode 1. Yeah. Well, episode 1, actually, I think the whole computer crashed because we were just figuring out how to like get all the audio data, and we had really high quality audio back then.
Yeah.
And Juan just got his new PC set up, and it had all this RAM and all these crazy features.
Yeah.
And doing all that tech at once dumped all of the data pretty much, and we lost all the episode 1.
Well,
But it was minutes. So.
but it was rather poor, so it was.
What was
we
was
decided we're just gonna start with episode 2.
episode 2? Okay. So we're not allowed to know what was the content about, the episode about.
It was just talking about expectations for the show and
okay.
what we want to get out of this. Mostly, yeah. It was kind of a soft introduction to the Eigenbros this brand.
There definitely was for sure no plan at all for episode 1.
Nice.
No, not at all. No, we just went in blind.
You're not missing anything.
We put the board and said, "Let's figure it out. What's going to happen?"
That's nice. Okay, cool.
Yeah. This is much more exciting, I promise.
I don't do a lot of games. It's just like this kind of puzzle stuff. Sometimes I think it's useful. It's interesting to see also, whether these. A lot of people think that these are really great educational tools as well for people getting into quantum computing. Because they kind of get you thinking about the intuition behind the gates and the circuits without really having to touch the math, which is sometimes scary for people who, they haven't done that for a long time. But yeah, so in this puzzle, just for you to get a bit of practice with superpositions, right? And so you kind of see here that actually your initial state is a 0-0 state, so you just have one ball, but the target state is you need to have this ball split into 2 and end up in 2 different states at the same time. So
What's the 0-1 and the 1-0 then? What's going on there?
they're empty, so you shouldn't get any those, you shouldn't get your system to fall into those states. So Terrence, you're quite right at the beginning when you mentioned about the Hadamard gate being the one used. So that's my hint to start with.
Gotcha. Okay, so yeah, let's throw a Hadamard on bit 1 if we can. Let's just see what happens.
Yeah. So if you put a Hadamard gate here.
So you want to go to 1-0.
So what this has done is that your first qubit, that's the one in the leftmost side of, so you start with the 0-0, right? So the first qubit is the first one reading from the left, turned into a superposition of 0 and 1. And so this means that your final state overall is split between the 0-0 and the 1-0, right? Because the second qubit you didn't touch, and so it stayed at the 0 state, right? But if you put them together, that's what you get, a superposition of a 0-0 and a 1-0. But you need to get the superposition of a 0-0 and a 1-1, which is, by the way, a Bell state. So it's the sort of a canonical example of an maximum entangled state.
Gotcha. So let's put another Hadamard on qubit 2 and see what happens.
So if you do that,
Cool. But also,
we got everything now.
put it super max positions, Terrence.
So we need to chill out on the superpositions, huh?
I will give you I will give you another hint, because I haven't really introduced that. Is there's more gates in here. So you have also the control element, which basically allows you to say, yeah, kind of, is to say, apply a gate only if the value of the other qubit is in a certain state, is in the state 1. That's the default behavior, right? So just to give you an example, if I remove these hardmark gates here and I put the control, and then I put like a let's say a next gate, right? So that would only flip the second qubit if the first qubit is 1. That's why you get this crossing here. It means that if the first qubit is 1, then we're gonna flip the second qubit, and that affects this state, but affects this one as well, right? Because the first one is 1, and so it flips the second one to 0. That's why you end up here. So, but you see that it doesn't affect our state because it's a 0, 0. So the first qubit is in the 0 state, and so the control does not trigger the X gate, so to say. And so if I were to apply an X gate to qubit 1 before that, then it would actually do that, right? So, yeah. Now, the trick is what happens when you apply this kind of logic to a superposition. That's kind of my second hint here.
Okay.
So
you're suggesting control not gate. So what we're going to do is, okay, so let's think what we had happen last time. So when we applied the Hadamard, first time, it took us into a 1, 0. So then if we apply a control not to that after that Hadamard, then that should give us a 1, 1, right? Can we try that?
So you want me to put a control gate where?
On the, I guess it's qubit 2?
Here?
Whichever one is gonna flip qubit 2 to 1.
Okay, so you should. Oh, so what you probably want is to put the control here, because you want to flip qubit 2, right? You want to flip the qubit 2 is 0, and you want to flip it to 1. So does that make sense?
100%.
Cool.
It didn't do anything.
No. So you need to add the gate that you want to control for.
Oh, right.
We did it.
So you did it basically.
Yeah.
Heck
Good job,
yeah.
Terrence. Good job.
So
It actually made sense.
yeah, so with the control gates, you can basically target really specific states. Instead of, if you realize that if you apply gates to a qubit, it actually affects to at least 2 of the states, right? Because you've got like all the possible combinations of 2 qubit values. But if you apply a control gate, you're basically constraining and saying only the states that have like a 1 on the control qubit will get the second gate, the target gate, executed, in a sense. So that is the. You're ready for the
game, man. How can I?
Sorry?
How can we get this game?
Yeah, it's really cool.
So this game, if you go to I'll share the link later with you guys. If you go to the video, to the recording of these, there's a link in the description to get the game, or you just Google Quantum Odyssey. It's a game by Quarks Interactive, and it's the only game they've released so far, basically. And so you go there, you download the game. It's, again, as I said, free to download. You can play the first. You have actually the whole puzzle creation is included for free, so you don't actually have to buy the game for these. They're now building also a lot of social stuff to this, so you can create puzzles and challenge your friends and stuff like that. But if you want to play the full game, the full experience, that basically shows you. Let me see if I can show that real quick. So this is the introduction to Quantum Odyssey comes for free. And then if you want to have access to the fundamental laws of quantum mechanics, to applied algorithms, and to thought experiments, those are puzzles which are really well crafted by people who know their shit. And then and so they and you have like a voiceover that talks you through the puzzle, introduces your concepts, and there's like a full-blown encyclopedia that also you can go and check different definitions, about like quantum mechanics and quantum computing and stuff like that. I'm not opening them because it just will take too long, I think, to load, and I just don't want to crash the the stream. But that's the idea. And now they're constantly adding new content to it. So they are now building a Grover's algorithm, like a Grover search module, just specifically about this algorithm, which is also really good, because one of the things that this game has is that the visuals. So, and let me open your final puzzle. So the visuals, right, is you see the state evolution, and when you apply a Hadamard gate, for example, followed up by another Hadamard gate, you can see the interference effects that happen between the different states. Which usually, when you do the math, if you just do like, take your wave function and multiply it by like whatever operator, like the matrix of the Hadamard gate, like the math basically just glosses over the interference, because it's just part of the way you add things up when you multiply rows and columns. And so you don't see that, right? And a lot of people just go and jump ahead with the math, and then they really don't see and understand or kind of see the fundamentals of what's going on under the hood. So I think that's why this game is really it's really cool. I personally really like it, so recommend definitely. Now, yeah. Go ahead. No, I was just gonna say. Sorry, go ahead.
Yeah.
that's the lag.
You got it.
Go, Terrence. What you got to say, man?
All right, I was gonna say that this game seems like it'd be very useful when I was an undergraduate.
The same way. This is amazing.
Yeah, I think it's really cool for both people who are getting into the field, but also people who just want to refresh some concept and maybe try to get a bit more intuition behind this. As I said here, I think I can open the encyclopedia. Let me see. Yeah, so you have like you have a bunch of like they explain you a lot of the mechanics of the game. A lot of stuff about cryptography. There's just a bunch of different things in here that are useful. If also from a pure quantum mechanics perspective. Let me close these.
Nice. Yeah, that's amazing.
Yeah, so it's pretty cool. I think the game has been under development for like more than a year, I think. So it's and also they are working on a math overlay. So if you really like the math type, you can also just check in here and actually see the state vector, how it changes and stuff like that. So and you can see the tensor products and things like these. So really cool stuff. Really cool stuff for both beginners and advanced. But
I was going to ask, when do we see Dirac's ghost? When do we when is that chapter coming in?
Sorry, the what?
Yeah.
I did. Sorry, I didn't hear that.
Dirac,
Dirac's ghost.
Yeah. Famous.
Are you familiar with Paul Dirac?
Well,
yeah, Dirac. The
science, so maybe.
No, but I mean, it's the guy who invented the notation for the bracket, right?
Yeah.
Yeah.
Yes, exactly.
Yeah.
It's gonna be a final boss game.
the final. Yeah, exactly. You gotta face. You gotta also fight Schrodinger's cat and yeah.
Exactly. There we go. See, we're giving the
Heisenberg's
great
gonna be in
idea.
there somewhere.
Yeah, Heisenberg and Einstein comes in and he's like, "This is all fake. It's not real."
I don't hear on you. Wake up.
Yeah, Einstein is one of the bosses of quantum mechanics. He doesn't believe it.
He's definitely the final. Sorry, Daniel. I'm sure.
No, it's all good, man. Quantum jokes are quantum jokes. We have I have a Discord server, and there's like a quantum memes channel, and it's also the quantum memes are also fun. But anyway, in this game here, so I'm just for the puzzles, just playing with 2 qubits because it's a bit more manageable. But you can actually have up to 5 qubits, which basically gives you 32 laser lines like that. So So I think I haven't completed the game myself, but I think that the final the final learning levels can probably be quite challenging. So, final puzzle. Yeah. So
At the end of this, I feel like I'm gonna have a galaxy brain meme moment where like my brain is just shooting rays of light at these qubits.
Qubits, exactly. So, huh?
So what should we do? We're trying to.
Okay, so you should basically that's your target state, right? You have to get to a state where it's an equal superposition, so you're in all states, but then each element has a little bit of a different phase.
Ooh, green, yellow, and red. Yellow
Exactly.
now.
So you've learned about the red, you've learned about the green, but now there's the yellow one. Yeah, we can also zoom in and out and speed up.
I know when we threw 2 Hadamars in there, we were able to get all.
Yeah, so that's a good idea. That's a good idea as a first step. So I think that we can do that. So if we threw the 2 Hadamars like you did in the war map, so now you get a yeah. So that's a good
way to do it. But I know it does 4 blue balls. So.
Yeah.
Yeah, so it's 4 blue balls because your initial state was 0, 0. So that's kind of the way that the Hadamar works. That when you apply Hadamar to the 0 state, it turns into the 0+1, which is a blue ball. Yeah.
Okay, so I know I see the green is supposed to be the 0, 1.
Mm-hmm.
So what do you think about? We haven't used the Y yet, have we? Can we throw the Y on?
No. The Y acts on 1, right?
So the Y acts on the states that have 1 component. It acts to the 1 component, right? So now you have qubits. You have your state is spread across all the possible states. So I mean, I can just drop it and then you can see the effect. So qubit 1, for example.
Oh, we got a yellow now.
Interesting. Okay. 2 yellows and 2 greens. Interesting.
Look at Qubit 2 instead, right?
Okay. Can you do that, Daniel? Throw the Y gate on Qubit 2.
So the Y gate to throw it away?
No,
put it on Qubit 2 instead.
On Qubit 2 instead. Okay.
Ah. Okay.
Not bad. Not bad.
We got 2.
You got two right. Yeah.
Okay, but that could change.
Remember,
one of that. I don't know if we.
So remember, there's a technique that you saw in the war maps that allows you to target specific states, right? Just dropping in a hint here, but it's not maybe trivial to see.
The C probably is what he's saying.
Yeah.
But remember, you're dealing with you're dealing with phases, right? So the C naught, like if you control a C naught, it's just gonna flip beats. Which, if you flip 0s and 1s, you'll just move the colors around probably. But you can try. It's just
True. So control the phase.
Oh, we didn't ask what is the
what's the
I?
I?
Yeah.
Oh, the I is the identity. It just means do nothing.
Oh, okay.
Yeah.
Unitary
Well,
operator.
that ain't good. The S is what I'm thinking. What's the S to? Forget.
Let me check. Okay, so the S adds a bit of a sort of a half. It adds like a 90 degrees phase to the 1 component. So this means that if you have yeah.
I
was gonna say, can we put an S on the qubit 2, maybe?
So
Oh,
you almost got that's a good move. It's not a bad move. Like the thing is, remember, because you're applying it to qubit 2, it applies to all the states that have a 1 in qubit 2, right? So this is this state, the second, and the fourth.
Oh, I wanted to do it for. Oh,
so we got half of them though. We got the red and the.
right. So if it's got a 1 in qubit 2, though, but just think. So if we did that for, if it had a 1 in qubit 1, what would happen? That would maybe we want to leave that because at least we have that half. So can we flip maybe the qubit 1's back somehow? So let's think. We plot it to where it has a 1. Qubit. We need something with a. We need something where it only works for qubit 1 with a 0 in it.
Exactly. So think about is there anything between the state 0, 1 and 1, 1 that differentiates them uniquely? Like what's the difference between these two states?
0, 1, and 1, 1.
Like, make
Let's think.
Yeah, well, I'm not sure what you mean.
Yeah, so I mean, it's even like just take a look at the numbers, right? So the second qubit is the same, but like the first qubit is not, right? So
how would you flip that?
So how would you just flip? How would you just apply this gate for a qubit where the first, like for a state where the first qubit is at the in the state 1?
I'm thinking we use the Y again.
Where?
In the first qubit. I'm just winging stuff. I'm just, you know.
You've
followed my.
So remember how you created the Bell state, right?
Yeah. Which is the 1. Oh, which is the 0, 0 to the 0, 1. How do we do that though? We did it with we did it with a single Hadamard, right?
No, we did it with 2, I think.
So you did it with a single Hadamard. Yeah, you did it with a single Hadamard, but then you had to make sure that you only move the state 1, 0 to 1, 1, right? So and you.
Oh, with the poly X.
Yeah, exactly. But you controlled it, right?
Oh.
Ah.
Thanks. So we went from 0, 0 to. Wait, we went from 0, 0 to 1, 0. So with this one, if we go to 0, 0, 1, 0 with the Hadamard, what's going to happen is we need to change it not to 1, 0, we need it to be 0, 1. Yeah, so how would we do that one?
We got to control. We got to throw control on it.
You have you only have a control that controls on the state 1. So how would you control on the state 0?
No, let's go to the chat. Here we go.
Help us out, guys.
Come on, any quantum computing? I'm just kidding.
Can we just throw a Hadamard on there at least so we can see what happens? Let's throw a Hadamard on qubit 1. How about that, Daniel?
So the Hadamard in qubit 1.
Yeah,
here?
Yeah. Does it matter where you put it?
Yes.
It's a different pattern, yeah.
Yeah, you get a different path.
So now you've because of the way the phases were distributed, you've destroyed some of them. So you no longer have like an equal superposition after that.
Remove it.
Take it away. Yeah, this game is tough.
Oh, this one is the final boss, huh?
Yeah, that's a.
I was saying this was the easy mode.
Shit.
Daniel, give us a hint.
Okay, so remember remember what you did in one of the first warm-ups, which is like you sandwich something with the X gate, right? Like it's so if you have a control, right, that only controls on the state being in the value 1, right? How would you tweak that so you can use this control to control on the state being 0?
Well, you would do the operation. I think we did the operation to flip it, right? And then we
Yeah, all I can think is if you flip the 0 to 1, then that's like so many steps.
and then lock it, and then no.
And then you're not wrong. It's so the trick is to make sure that you're not touching other states, right? But if you think about what if you sandwich the control? So let's say you put a control here, right? Sorry, no. What have I done here, right? So now this only, of course, affects the 1-1 state, but you want it to affect the 0-1 state, right? So if you take the X gate and because you know it's a 0, so first you take it to 1, so you flip that qubit, right? Then you apply your control phase, and then you flip your control qubit again, so it goes back to the 0 state, right?
I thought that was going to be too convoluted, but I guess it works.
Yeah. It's let me see, and that I should just reorder things around. There you go. Oh,
What? Oh, it went the wrong way.
it went the wrong way. Maybe actually, yeah, but actually, if you flip these and these. Oh, wait a second. Maybe it's not even needed. This one. I think I might even have gotten it wrong. Oh, there you go. Okay, so yeah.
Look.
Somehow it works.
See that one
It's
blue.
so close. That stupid blue. that stupid blue needs to get blue. The yellow needs to get blue. So how do we do that? That's why it's like one false move though. You change the whole thing.
Yeah, exactly. So you can, but you can always. So but the sandwiching technique works. Usually works, right? So if you just focus on, you know, for example, that like what. So if let's say, how would you switch the red one to blue? This one, the 1-1.
I don't want. Why would you want to switch the red to blue?
No, it's a question. Like, if this was a goal, right? You know, you can apply a control phase to the 1-1 state, because the control qubit targets the let me see, because no, I lost the cursor here. Okay, so the control Z would actually target this state, right?
It wouldn't control the 1-0 as well.
It would not, because the Z gate, for example, only acts on the 1 component, so it doesn't change the 0 component.
Mm-hmm.
So with the control Z, right, you would flip this one from red to blue, but you want to do that with a 0-0, right? So you can always apply sort of the same technique. It's like you do a computation, like you flip these 2 qubits to the 1-1 state, because you know how to work with this state, and then you uncompute, you kind of undo your original operation that took you there, so you go back to the 0-0 state, but you have changed the phase in between, right?
Okay. So we need to control again.
Yeah.
So if we use a C as a control and do an X flip.
So if you do these, if you do these, yeah, that's not wrong. So if you do these, that's actually, but that's gonna do what we just said, right? So that's gonna, oh no, a control X you want to do, or what? Yeah. What do? Okay. So that's gonna flip you things. Oh, yeah, but that's yeah. No, okay, but you had it. You had it right before, so that didn't make sense. You just flipped the, because you flipped the 1 1 to the 1 0, and at the same time the 1 0 to the 1 1.
So instead of an X, what do I need? Maybe a Y. Can we try a Y?
So you need a gate. You need a gate that doesn't flip the qubits, right? That doesn't flip the 0 1 values.
Okay, throw the Y away.
We need that on the first gate, right? Because it flipped green and blue. First.
Oh, you're saying the control now needs to be the qubit too?
Well, because it flipped the.
All right, try that.
Well, hold on.
No, we don't want that.
Hold on. Let's think about this.
We just want that 1 0 0 to flip.
So the.
Yeah. Okay. So now, Terrence, let's think about this. So we have Daniel can convene if he wants to.
I know 0 0 will switch with the Hadamard gate to a 1 0, right? But how do we control that Hadamard? I guess can we do a qubit? Can we do a control knot on qubit 2 and then a Hadamard on qubit 1?
All right.
Try that
Go
one.
Terrence. I want to break this down.
So you wanna have the control on the second qubit, right?
Yeah, and then I want a Hadamard on. Yeah, I want a Hadamard on 1. Okay, that's just. This is like.
Maybe you got interference here.
All right, throw that.
Hold on. No. Hold on. We haven't seen it go to fruition.
It's gonna go to hell. Trust me.
Oh yeah, you destroyed one of the stakes.
Take that Hadamard out of here.
I'm sorry.
One more time. So, no, we're just shooting darts here.
Yeah, but it's it's.
I keep forgetting what Axum is.
That's how you build intuition and this kind of stuff.
But,
It's
okay. Oh, me and Terrence, we're intuition guys, so we that's our bread and butter. But the Hadamard gate, right?
Mm-hmm.
It flips the 0
Well, no,
0.
that's a poly X.
No. The first operation position. So we go 0 0 1 0, right?
Okay.
And then in qubit 2, we're going. I guess we're making it so it's 0 1 and 1 1, right?
Mm-hmm.
And so that's all fine. And I guess should we just work from the bottom up again? What do you feel like doing?
What do you mean?
Let's just
everything.
Let's just go with the first two operations.
We're like so close.
Yeah. I can give you a hint. I mean, you're not. I think you're in a good place right now. So I would not undo any of what you've done. So I think you're in a good place. You only have to figure out how to switch the phase of the 0 0 element to be yellow, to be blue instead of yellow, right? So you need to target that specific state.
Put an X on the
Y control on the
qubit 1.
On the qubit 2.
No, qubit 1.
Okay.
Where do you want to?
Let's do that, Daniel.
Which gate again?
X on qubit 1. Gate 1, the qubit 1.
Yeah, qubit 1.
An X gate.
On X gate after control.
I feel like I tried that. We'll see.
Did?
I don't know. I think I did.
Did you?
And all hell broke loose.
I must have been zoning out trying to understand.
Okay, so let's look what that did. So that changed the bit to 1.
Did you really try that?
Changed the first bit to 1 to everything. That's the problem. So we need to control somehow.
Yeah, undo.
Yeah, I don't know how to use this control knot.
So I'll give you another hint if you want. So if you have just focus on this operation here. So if you do a control Z, right? So what this is going to do is it's going to change the phase of this element here, right? And now it's going to change it from red to blue, right? But you want this to happen to this element here, right?
Yeah.
So how would you do that? And the hint here would be, remember that there's a gate that just just flips things around, right? Like just switches the balls from one place to another.
Switches the balls from one place to another, or for switches the phase.
No. So there's a gate that basically will just shuffle your balls, right? So it's probably the wrong type of sentence, but like it will just move things. It'll just move things around, you know.
All right.
Okay, let me start.
Okay, so you put that blue ball on 0, 0. So now. So change that 1, 1 to 0.
I'm gonna get some pen and paper here in a second. tired of watching Terrence guess.
Pen and paper, that's bad. You can guess too, man.
No,
I don't see you chiming in.
Because I was gonna break down, like, I guess mathematically, operationally, what we're doing. Because, like, okay, we flip all the states in the first step, right?
Yeah, you know what we need?
And then the second.
I think we need like a description of what all the gates do again.
Yeah. Okay. So yeah. So I can give you that. I can give you that. It's easy. So, I mean, let's go gate.
Cover over it.
Let's go. So let's go gate by gate, and I'll try to give you sort of an intuitive overview of what they do, right? So, what the Hadamard gate does, right, is it takes your it basically takes you from the state 0 to a superposition of 0 plus 1. Right. So when you apply this gate to the state at the beginning, to the both qubits, right, it takes you to an equal superposition because it's just a combination of all of the states. So that's a good step. The rest of the gates, what they do is they either change the phase of the one component, so they change the color, or they flip the bits from 0 to 1 and 1 to 0, right? So that you see this with these lines being crossed, right? So the X gate is 2 blue lines crossed, so it means that it flips the 0 to 1 and the 1 to 0. The Y gate, they have an additional color because on top of flipping the bits, it also adds a phase to them, right? So this is a bit more complicated gate. But the Z gate, essentially what it does is it adds a phase to the one component of your state. So this means if your state is 0, 1, is 0 plus 1, right, in one qubit, it will add that relative phase. If you're here, right, if you apply a let's see if I can move the right gate. So if I put the Z gate, just to illustrate that, in qubit 1, it changes the phase of the states that have a 1 in the qubit 1, right?
Where's the gate that does that 0, 0?
Exactly. That's what you have to construct. So that's what I'm trying to walk you through now. So it's the thing is you can control a gate to basically target a specific state, right? So you say, I want to do that, but only for the case where the first qubit is 1. That's why you put a control in the first qubit, right? So what this gate here gives you, as it says, only if the first qubit is 1. Apply the Z gate. Now you have two states in which these can apply, right? The 1, 0 and the 1, 1, they both have the first qubit to 1, but the 1, 0 state has the second qubit to 0, and so the Z gate doesn't have any effect on that, right? Because it only affects if the qubit is 1. So that targets this one here, right? Now, but you don't have a control that would act on 0. But remember that from the warm up, what you can do is you can sandwich the control with 2 X gates. So you take your control, you flip your control from 0 to 1 and 1 to 0, then apply the gate that you want, and then you switch it back to 0 because you wanna keep the state that you originally had, right? So if I do that here, right? If I apply an X gate here, and then another X gate at the end. So what this does is it just adds this mesh at the top, at the front and top and the bottom. So it just basically takes all your states that like, it flips the first qubit of your states, right? And then applies the control Z, and then it flips it again. But that doesn't do the job, and it's because it still only acts on the state that you on the states that have a 1 here, right? So I can show you how this is done by, if you do also a sandwich on the qubit 2, you're basically taking your state, your 0, 0 state, you're taking it to the 1, 1, then you're applying the phase shift, and then you're switching your 1, 1 back to 0, 0. But you're carrying the phase shift with you, right? Now this hasn't switched it to blue because it was red and it's sorry, it was green and it applied a red one, right? So I've basically shifted it too much. So you just basically need to pick another gate that does a smaller phase shift, right? Which, as an example, that's the S gate.
Nice.
I think that should make it.
All right.
So if we fail this one, I think we're gonna have a really bad time.
No, but that's a complicated one because you kind of have to you basically have to apply a lot of these sort of little tricks that allow you to, okay, if I have a gate that I know that it modifies the 1, 1 state, I know I can flip both qubits, do that gate, and then flip the qubits back. And I shouldn't worry about whether I affect other qubits or not, because when I flip them back, everything is going to go back into its original place. So as long as I know that I'm targeting just one qubit in between the sandwich of X gates, then it's all going to be good. It's going to do the thing that I want it to do, right? Yeah, but I mean, that's it. It was cool to kind of see you guys try to walk through the puzzles. I think that's also one of the things. I mean, that's also one of the things that I really try to do in the channel, where you got a lot of stuff out there, people uploading content about physics, about math, about programming, where it's like everything is so well prepared that it just seems so easy, right? But when you do these without really having prepared stuff, without really having thought through things up front and having nothing ready, you really show sort of the raw process of how you would think about this kind of stuff. And yeah. It's usually me on the channel, just submitting myself to the pain of trying to solve a problem without having prepared up front. And so I thought it would be cool to see other people suffer from time to time. So I think it's I'm really happy that you had the time to join, because I think that's really valuable for people to see how others think through these kind of puzzles. Yeah.
Well, we are glad that you're guinea pigs today again. Just hopefully people are all dumb now after this.
No. This is good. This is good. We are all silly people, so.
I have a feeling, though, this ranking system is kind of broken, though. We still got 5 stars after taking all of that.
I think that's because it's a custom puzzle. So if you go through the actual learning levels, I think it actually has something that makes more sense. But this is just a custom puzzle, so I really haven't put all the. You can define the difficulty level, you can define some other kind of goals and stuff like that. So you can do a lot of these things with the game. But yeah. Yeah, that was. Sorry?
I just on when we play the game with a couple more levels, and we'll really show you what that was.
Yeah, I mean, the game really takes you from from zero, from scratch, to actually doing real algorithms. So you're gonna do Grover's algorithm for search. You're gonna implement other kind of algorithms just by learning step by step. And it's not like you're on your own. So you've got like a character that goes with you and explains you everything, and sort of you're building up on these as well. And as I said, the team is creating a lot of content continuously, and the game is not just like a static set of puzzles, but it's changing. And Yeah. So I really,
I have one suggestion for the development team.
yeah.
So if they can get Sean Bean to do the narration, that would
Who's
be
Sean Bean?
Sean Bean, the Game of Thrones, Lord of the Rings.
Oh,
Pictures coming guy.
okay. Okay, I haven't seen Game of Thrones yet.
That'll be.
That'd be amazing. Just him saying, this puts this into 26 something cool.
something cool in with his voice. Yeah, the person that does the I recommend playing the game. The voice that is in the actual levels is also a really nice voice. It's a really nice voice. The music is amazing. The graphics are amazing, and they really create a good atmosphere for you to get into the game. So and I know they are planning to release another game at some point in time based on something which it's a bit more like real life action kind of. So you really will just be moving around some lab and then doing some weird shit with like different lasers and stuff like that. And so this is kind of like their first attempt at this. So
Are there any plans to bring the game to like iOS or Apple or Android?
could you say that again? I didn't hear you well. The voice didn't come through.
Are there any plans to bring the game to Apple or like?
Oh yeah. They're working on this. So this is a Windows release first only, but they're working on this. Yeah, definitely.
Wait, this is the perfect game that I would just play.
Yeah.
It's so cool. It might help.
Wall too.
Yeah, it might help for just building. I mean, I think it's great to build intuition on new mathematical operations, mechanics and stuff. And yeah, I was just in awe the whole time, just being like, wow, this would have been so useful to have in my undergrad.
Yeah.
That's cool. And actually I'm playing also the low resolution version of the game because otherwise my machine would just die in a second. So it has much nicer graphics, and it's all much, it looks much better when you're playing it just not streaming at the same time. Well, at least with a more powerful machine. But yeah, you're right. It's a great. I think it's a great. It's just a bit, it's not like the traditional way of learning the typical circuit stuff because, as I said, the math really glosses over a lot of the details. And so I think that's definitely worth a try. And just once more, the discount code is in the description, and it's going to be still active for the next days. If anyone wants to buy the game, it's a 50% off, and all the revenue goes to the Unitary Fund, which is basically a fund that actually invests in small projects about quantum computing and quantum education and stuff like that. So you'll be supporting both the game team, the Unitary Fund, and and also thanks to the Eigenbros for joining. And definitely check out the podcast, which is also everywhere. And I watch it on YouTube though, because I'm more like I don't know. I like to have both options.
Yeah, he loves the video stuff.
Yeah, I think it just adds, if I cannot watch the video, it's fine. I'll just, as I said, I'll be doing the dishes and just listening to your both amazing voices, just discussing about stuff. And you guys really have podcast voices. It's I don't know how you do that, but and then if I'm a bit more flexible and I can watch the video, it's always nice as well. So keep up with the good content, and thanks a lot for joining.
Thank you.
Thank you, man. It was a pleasure.
Yeah.
Cool. Perfect. So we'll just, I'd love to stay in touch, and then, thanks. I think I'll just be stopping the, so there's some people in the chat that are thanking you because I don't have the website app, but I have the YouTube, and there's a lot of people thanking in the chat for you guys. There's some people thanking. So yeah, cool stuff. Good. Then I'll be stopping the stream.